Hello everyone, my name is Asma Saidi and today I will be presenting my capstone project titled Improving Medical Diagnostic Accuracy and Efficiency with Artificial Intelligence. Here's what we will cover today. I'll start with an introduction to set the stage, then dive into the topic itself, what AI in medical diagnostics really is. After that, I will walk you through the three main problems I identified, and then the solutions I propose to address them. Finally, I'll share my analysis of how I arrived at these solutions and why they are viable. Let's start with why this topic matters. The purpose of my project is to look at the current state of artificial intelligence in medical diagnostics, and especially to examine the problem that AI is uniquely suited to solve. But why is this so urgent? Our healthcare system are under enormous pressure. We have an aging population, more chronic diseases, and an explosion of medical data. At the same time, the number of clinicians is not growing fast enough. In fact, according to Joe et al., the healthcare AI market is projected to hit $188 billion by 2030. That tells you just how much potential people see in these technologies. So, what is the core challenge? Modern medicine is facing a major crisis: inefficiency and inaccuracy in diagnosis. Our traditional diagnostic processes were built for a different era. Now we have so much information that it is overwhelming. But here is the central argument of my project. The solution is not to replace doctors with machines, but to strategically integrate AI into clinical workflow. AI can take over repetitive tasks, support better decisions, and help manage the complexity of modern data. And of course, we can't just deploy AI without thinking. We have to consider ethics, regulations, and how to implement these tools responsibly. Now, let's get into the topic itself. When I say AI in medical diagnostic, I'm talking about using machine learning, especially deep learning, to analyze complex medical data. This is not about robots doing surgeries. It is about algorithms that can look at an image, a genomic sequence, or a patient record to find patterns that help clinicians make better decisions. What makes today's AI different from older computer systems? First, it has automatic feature extraction. That means it learns what to look for without being explicitly programmed to do it. Convolutional neural networks, for example, can pick up edges, shapes, and subtle textures that signal disease. Second, it is scalable. An AI can process thousands of images in the time it takes a human to review one. Third, it is consistent. It doesn't get tired or distracted, and increasingly, this system can integrate multiple types of data, like combining an MRI with genomic information and lab results. Finally, there is a big push for explainable AI, so that clinicians can understand why AI made certain recommendations. To really appreciate where we are, it helps to look at how diagnostic technology has evolved. In the past, we relied on clinical examination, then lab tests, then basic computer-aided detection. But those early systems were rule-based. That means they couldn't learn from new data. Today, with deep learning, we have systems that continuously improve as they see more cases. This is a fundamental shift. So why is this the right moment to talk about AI in diagnostics? Three reasons. First, the technology is mature. It is already being used in real hospitals for things like mammography and retinal scans. Second, regulators like the FDA has approved hundreds of AI medical devices. And third, the pandemic pushed healthcare systems to adopt digital tools much faster than anyone expected. Now, let's get into the problems. I identified three interconnected challenges that are crippling medical diagnostic today. First, inefficiency and workload burden. Clinicians are overwhelmed. For example, a pathologist reviewing prostate biopsies might have to look at nearly 600 slides, taking over 15 hours. Radiologists can spend minutes per scan, but they can have hundreds to review. This leads to burnout, which in turn leads to more errors. Second, subjectivity and diagnostic variability. Two different clinicians can look at the same patient and come to different conclusions. This is not just about skill, it is about interpretation. In some cancers, expert pathologists only agree about half the time. Third, we simply can't keep up with the data. A single CT scan can have millions of data points. Genomic sequencing generates petabytes of information. Our brains just aren't built to process that much data and find subtle patterns. Let me give you some numbers to show how real these problems are. On efficiency, the US is projected to be short more than 20,000 diagnostic specialists by 2032. In Europe, half of radiologists are nearing retirement, and many countries already have too few. And the cost of delay is staggering. A 4-week delay in cancer treatment increases mortality risk by 6 to 8%. On variability, consider that in some cancer diagnoses, pathologists agree only 48% of the time, and medical errors overall are the third leading cause of the death in the US. That's almost 440,000 deaths a year. And on data overload, healthcare data is growing at 36% annually, but the number of clinicians is not. Our conscious processing bandwidth is just 10 to 50 bits per second. That's like trying to drink from fire hose. So what is the answer? I propose a 3-pronged approach using AI. First, automation for efficiency. Let AI handle the routine high-volume tasks so clinicians can focus on complex cases and direct patient care. A great example is a deep learning system for rib fracture detection. It cuts reading time from 5 to 7 minutes per case down to just 3 to 5 seconds without losing accuracy. Another example is mammography AI that can pre-screen normal studies, which reduces radiologist workload by up to 70% while actually improving cancer detection. Second, decision support to enhance accuracy. Here, AI acts like a smart assistant. In neurology, AI can help segment brain tumor from MRI scans, a task that is very time-consuming and varies between experts. When the AI and the clinician work together, the results are more accurate than either could achieve alone. Third, predictive analytics for early detection. This is where AI can be truly transformative. For example, a recent Harvard study showed an AI that can predict pancreatic cancer risks up to 3 years before traditional diagnosis. That could make a huge difference for a cancer that usually caught too late. But how do we actually make this happen? I suggest a phased approach. In the short term, we pilot automation tools in high volume areas like mammography. In the medium term, we roll out decision support system across specialties. And in the long term, we integrate predictive analytics into population health management. And these aren't just theoretical. There are real-world success stories. KCR Permanente's Advanced Alert Monitor, for instance, analyzes hundreds of thousands of hospitalizations to predict which patients are deteriorating. It reduced mortality by 16% and saves over 500 lives a year. Now, how hard is it to execute? Automation tools are the easiest. Many are already FDA approved. Decision support is moderate because it needs to integrate with electronic health records. Predictive analytics is the hardest because it requires huge, high-quality datasets and extensive validation. But the fact that major medical centers have already done it shows it's possible. Now, let me walk you through how I came to these conclusions. As an IT student, I follow tech news daily. Over the past year, I kept seeing stories about AI in medicine, such as new FDA approvals, breakthrough researches, and hospital implementations, so I decided to dig deep into this topic. To verify the problems, I found studies that measure clinicians' workload, studies that quantify diagnostic disagreements, and research in human cognitive limitations. I also looked at workforce shortage projections from organizations like the AAMC, so the problem are well documented and urgent. And the solutions, they work because they directly target each problem. Automation addresses inefficiency. We have the rib fracture system and the mammography AI as proof. Decision support tackles variability. The brain tumor segmentation study shows how human and AI together beat either alone. And predictive analytics solves the data complexity issue by finding patterns humans can't see, like the early warning signs for pancreatic cancer. But I also wanted to be clear that technology alone is not enough. We have to address ethical issues. Algorithmic bias is real risk. If an AI is trained mostly on data from one population, it may not work as well for others. That's why transparency and explainability are so important. The World Health Organization and the American Medical Association both emphasize that clinicians need to understand AI recommendations to maintain accountability. And regulations like the FDA approvals and EU AI Act are starting to put these ethical principles into practice. Finally, here are some of the key references I used. These come from top medical journals, health systems, and research institutions, which gave me confidence that my analysis is grounded in credible evidence. Thanks for listening.